So we're going to take a minute and apply the binomial theorem to stuff like probabilities. So like flipping a coin or true-false questions or multiple choice questions or really anything. So if you have two possible outcomes, you can either succeed or you can fail. So P is the probability of success and Q would be 1 minus P or the probability of failure. So basically, let's say if we have the probability of K successes in N independent trials. Now, independent is an important word here because none of what we're talking about applies if you have dependent. So if you ever see anything like what's the probability of E given F or something like that, that's dependent. We're just doing what's the probability of some event happening in general. Okay, so let's say that we have one trial of something like flipping a coin. So we can basically have one success or one failure. So to make that easier, we can say we either have T or we can have F, so true or false. Now, for two trials, we can either have two successes, or we can have a success and a failure, or we can have two failures. Now, we can actually, if you just kind of think about flipping a coin, you can get a heads and then a tail, or you can get a tail and then a head. So there's actually two different options there. You can get one success, you can have two half and halves, basically, for lack of a better way to say it. One true, true, two different ways to get one of each, and there's one way to get exactly two failures, okay? Whereas like here, there was just one way to get each thing. 1 and 1. Those look weird. 1 and 1. Okay, so let's say we have three trials. And again, we're flipping a coin or true-false questions or whatever. So with three trials, we can get true, true, true. We could get true, true, false. We could get true, false, false. Or we could get false, false, false. Now, again, you can probably look at it and go, well, actually, instead of getting just true, false, true, or true, true, false, we could kind of rotate where that F is. We could go true, false, true, or false, true, true. And then similarly, we can get false, true, false, or we can get false, false, true. So that's going to the idea that we can have one way to get them all, three ways to have two trues, three ways to have exactly one true, and one way to have exactly all false. So there's a couple of ways that we can kind of look at doing this. So this is starting to look a little bit suspicious. If you kind of think back to binomial theorem, and you might start to recall Pascal's triangle that looks like this. And what do we have here? But we have 1, 1, 1, 2, 1, 1, 3, 3, 1. So that's 1, 1, 1, 2, 1, 1, 3, 3, 1. So all of this is definitely intentional. Well, what's not intentional? I didn't do it on purpose, but it's not coincidental at all. So let's look at this again. So if we have one trial, let's say that we have a probability of success for true, so that's P, and a probability of success for false, which is Q. Okay, so I'm going to do this again. So I'm just basically going to say the exact same thing, but in a different way. So we can have true, true, and the chances of having two things be true are P squared, right? Because you have to have true and then true again. Now in the middle, we have false, true, or true, false. So for something to be false and true, it's PQ or QP. I said the same thing, but wrote it twice. So the first one would technically be QP or PQ, and false, false would be Q squared, like that. Okay. Yay! Okay, so then we could do three trials, and I think you might see where I'm going here. We can go true, 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 which has a PQ probability, because I have to get it right all the time. Two trues and a false, or would be P squared Q, and then if I go like this, or if I move this around, I'm still just going to get P squared Q. If I go true, false, false, or false, true, false, or false, false, true, I'm still going to get PQ squared. All of these are going to be PQ squared, and then if I go false, 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 I get Q cubed, like that. Got it? Okay. So the probability of getting three falses is Q cubed. Okay, so what you're seeing here is kind of a layout again where you have P, so we have P and Q. So I could say I have P and Q. Actually, let me write this off to the side. That may make it a little bit more clear. So I have P and Q, and here I have P squared and 2PQ and Q squared. And here I have P cubed, 3P squared cubed, sorry, 3P squared Q and cube sound alike, and 3PQ squared and Q cubed. All right, so as you're kind of looking at this, there should be a part of your brain that goes, well, if I just kind of put a plus sign here, what do you see? That's your binomial theorem again, right? That would be A plus B, or P plus Q to the first. This would be P plus Q squared, and this would be P plus Q cubed. So as you're going through this, it kind of blows my mind that that whole Pascal's triangle thing is going to pull all of this information into it again for something as simple as looking at independent trials of either a true or a false. And the true and the false don't have to be equal. You don't have to have 50%, 50%. It could be 25%, 75%. You know, but it shows you the probability and the different combinations that you can do to get that. So if I'm taking a true-false test, the chances that I get exactly, let's say that. So let's say that we had a 3-flip heads or tails game. So what's the probability of getting exactly 2 heads? And we can pretend that heads is true. Okay, so there are, looking at our picture here, there are 3 ways. So there are 3 ways to get exactly whatever you calls it. Oh, wait, I circled the wrong one. There are, there we go. There are exactly 3 ways. It's still the same answer, but that's okay. There's exactly 3 ways to get it. The probability of being successful is P squared, and the probability of not being successful is Q. So this works even if I have like a weighted coin. So if heads and tails isn't exactly even, you know, if I have a better chance of getting heads, maybe it's a bad coin, then I would just put that in there. So the 3 represents the number of combinations. I can't spell. There we go. That's the number of combinations. P squared is going to give me the probability of exactly 2 successes, and then the Q would give me the probability of exactly 1 failure. So what's really cool is that in general, the probability of getting exactly K successes in N independent trials, we should say that again, in N independent trials, would be to say that it's N choose K, because that tells you how many ways there are to do it, and then there's the probability of exactly K successes, and this is the probability of exactly Q failures. And that just totally blows my mind. What blows my mind even more is if you go and you try and apply this to, well, what happens if you just go guess on a lot of tests? So that's pretty cool. So let's go play with that. So given say we have a true-false test and we have 8 questions and we're just going to randomly guess. So this is kind of like a flipping the heads and tails kind of thing again. Then what's the probability of getting exactly 1 right? So if we kind of look at our little formula here, it's going to be 8 choose 1, and then you have 1/2 chance of getting exactly 1 right and a 1/2 chance of getting specifically 7 wrong. Now 8 choose 1, we can either use, there's a lot of methods you can do it, but this is 0, 1, 2, I mean the answer is going to be 1, but 6, 4, 1, I'm going to write these down because we're going to need them later. But this is for the lazy. I'm going to run out of room. 15 and 1. There we go. I didn't think you wanted to watch me write all that out. But there's your Pascal's triangle for 0 through all the way down to 8. Now resist the urge to go that 8 choose 1 is the first one. That's actually 8 choose 0 of getting exactly none of them right. And it really doesn't matter if you're looking at exactly 1 right or exactly 1 wrong, because they are symmetric from left to right. So it doesn't really matter which one I'm counting as right or wrong. But this is N choose 0. This is N choose 1. So the answer is 8. I could also have gotten there because I know that 8 choose 1 is 8 factorial over 7 factorial times 1 factorial. So that also gives me 8. So I have that. and then times 1/2 to the 1 and 1/2 to the 7, so that's just 1 over 2 to the 8. So that's 8, which is 2 cubed, over 2 to the 8th, which is 1 over 2 to the 5th, not 25, which is 1 over 2 to the 5th, which is 1 over 32. All right, so you might be like, well, that's pretty cool because that means that I've only got a 1 in 30 chance of only getting one right. Okay, so then clearly the most logical question next, let's see, what is that 1 over 30? So that's basically 0.3125 or 3.125%. So you only have a 3% chance of only getting one question right. So it's totally worth just like guessing, right? Okay, so let's actually pretend that we're not mathematically illiterate, which is kind of a stretch, but it's cool, you know, whatever. And what we're going to say is, what is our probability of actually passing the test? All right, so to pass, you have to get 6, 7, or 8 right, like if we're assuming a passing is a 70% or higher on the test. If I want a 70% or higher on the test, because I want to pass the test, but I don't want to study, so what is my probability of passing if I don't study? All right, so essentially what we're going to do is we're going to sum going from k equals 6 to 8. So I can either choose exactly 6, choose exactly 7, or choose exactly 8. So you could write it like this. All right, so I've got 1/2 to the k, and then 1/2 to the 8 minus k. Okay, now anything that doesn't have a, well, I guess I can just look at this and I can say, well, 1/2 to the k times 1/2 to the 8 minus k is always going to be 1/2 to the 8. So I can just pull that out. So 1 over 2 to the 8th, and then the summation, k going from 6 to 8, 8 choose k. Okay, so I've got 1 over 2 to the 8th, and again, I can either use the, well, I'll write it out first. I can do 8 choose 6, 8 choose 7, or 8 choose 8. So I have to get all 8. I can either get 100, and an 87.5% or a 75. So this would be passing the test with a 75. This would be getting an 87.5% grade on the test, and this would be getting 100% grade on the test. Okay. Now we can either do this with the factorial method, or we can come over here and we can add our numbers. So this one, there's only exactly one way to get them all right. There's only 8 ways to just miss one, and there's 28 ways to miss, or to only miss 2. So here we go. So this would be 1 over 2 to the 8th times 28 plus the numbers I've already forgotten, 8 and 1. All right, that's going to get you 37 over 2 to the 8th, which gives you approximately 14% chance of passing. So it's one of those things where just like instinctively you want to be like, well, if I have a 50% chance of getting everything right, then I should have a 50% chance of passing. And that's like not it at all. You actually only have a 14% chance of passing, which is, yeah, should tell you to study. So this is also kind of cool if you're a digital logic person. The pluses are like ors, so I can either get 6 right, or I can get 7 right, or I can get 8 right. And then the multiplications are like the ands, like, because the only way to get exactly 1 right would be to get 1 right and get 7 wrong. And so that's where the multiplication comes in, because I have to get this many right and this many wrong, so you're doing multiplication. Whereas there's like different ways that I could do it, so I'm doing the addition. So if you're a digital logic person, that's kind of a fun little thing to put in there. So I know this video is getting kind of long, but it's really interesting, so it'll be fine. Also, it's super all related to each other. So this gets a lot worse with multiple choice questions, because basically what's happening is instead of having a half a chance of getting it right, now you only have a 1/4 of a chance of getting it right. So what we see is still kind of the same thing, where we have k going from 6 to 8. 8 choose k, and then, but now instead of having 1/2, we have 1/4 to the k, and 3/4 8 to the, or 3/4 to the 8 minus k. And so that means that we end up in all kinds of crazy trouble, because basically we have 28 ways of getting exactly 6 right and exactly 2 wrong. And then we have 8 ways of getting 1, or I guess 7 right, and exactly 1 wrong. And then we have exactly 1 way of getting all 8 of them right. So whenever you put all of that together, you end up with a number like 241 over 48, which gives you a 0.423% chance. That means 4.2 out of 1,000. So that point is not in the wrong place. That's 4.2 chances out of 1,000 that you're going to pass only an 8-question multiple choice test if you don't study. Okay, so that is something that's really, really crazy and kind of hard to accept, because you're like, but it shouldn't be that bad. So to finish off, where you can secretly go, yay, here's a weird question. So let's say 3/4 of the answers are wrong, right? Because it's a 4-option multiple choice test. So 3/4 of the answers are wrong. So what's the probability of getting exactly 3 of the next 4 questions wrong? Because you're like, well, 3/4 of the answers are wrong, then if I'm just randomly guessing, then it should be like basically 100% chance I get 3 of the next 4 questions wrong. Okay, and that's actually not intuitive at all. So, yeah. So just to make things more funner, in this case, we're going to call wrong a success. So we have 4, and we want to choose exactly 3 wrong times the chances of getting that many wrong times the chances of filling. Now, it doesn't really matter. I just think it makes more sense this way. So 4 choose 3. I can go up to my little pile. So 4 choose 0, 1, 2, 3. So 4 choose 3 is 4. 4 choose 3 is 4. 4 choose 3 is 4. So 4 choose 3 is 4. And then I have a 3/4 of a chance of getting them wrong and a 1/4 chance of getting it right. And if I multiply all that out, I get 27 over 64, which is actually only 42.1%. So this is definitely not intuitive, and this is why I pretty much hate statistics, and this will probably be my only statistics video ever, because statistics make me super sad. And this is supposed to be snuggly happy math time, not super sad, awful statistics time, and math and statistics aren't really the same thing. So let me show you this, just so you can kind of see how this math works. Let's say we have a 4-question test. The probability of getting all 4 wrong actually turns out to be 31.6%. And here are the rest of the numbers if you just work it out. So there's the 42.1, which is the number we just came up with. Now, in order to pass a 4-question test, you either have to get none wrong or only 1 wrong. So you, again, only have a 5.1% chance of passing. So you totally, even for a 4-question quiz, you absolutely have to study. And it's weird, right? Because you would think that you would have a better shot, and you just don't. So this is the most common grade that you could get, is a 25%, but you've actually got a better chance of getting them all wrong than even getting just 2 right, which kind of makes sense, but it just makes you sad. Now, these can get better by elimination, but we're just assuming these are all equal independent trials. So if you really wanted to know what's my expected value, or my expected grade, what you would do is you could say, all right, I have a 31.6% chance of getting a 0 on the test. I have a 42.1% chance of getting a grade of 25 on the test. I have a 21.1 chance of getting a 50 on the test. What would I call this? Oh, hold on. A 4.7% chance of getting a 75. And I've got a 0.4% chance of getting 100 on the test. And if you're really careful with your sig figs, that gets you an expected grade of 25. So your expected grade, if you go in and you just totally guess on a 4-question quiz, is on a 4-question, 4-option multiple choice quiz, your expected grade on the test is a 25. So I guess the point is, don't be surprised. But yeah, like, playing with statistics is all kinds of weird. I'm gonna go back to doing real math now.